I'm Fleshed Out Thoughts, and I love fleshing out thoughts for extended periods of time. And I'm building a full stack e-commerce platform for digital products and software services with Next.js and Supabase. This series is about the architectural decisions behind the platform, what I built, why I built it that way, and what I do differently. Today, we're going to be getting into authentication with Next.js and Supabase, session tokens, HttpOnly cookies, and TOTP. All right. Authentication failures are a category of bug where the damage isn't discovered until it's too late. A user session is hijacked. An attacker enumerates your user base. A credential stuffing attack succeeds against accounts with reused passwords. None of these announce themselves. You find out when someone reports their account was accessed, or when you see login attempts from IP addresses in 3 countries simultaneously. The right way to design authentication is to start with the threat model. What can go wrong, and what mechanisms prevent each failure, and then implement the mechanism. The common mistake is to start with the implementation and assume it's secure. I'm building an e-commerce platform with Next.js and Supabase. My authentication layer uses HTTP-only cookies for session storage, Supabase's built-in session management for token refresh, and TOTP as a second factor. This video is about why each decision closes a specific attack vector. 4 attack vectors that authentication must address. A session token theft via cross-site scripting. A script injected into your page reads document.cookie or localStorage and exfiltrates the session token to an external server. It's one fetch call and the session is stolen. The attacker logs in from any device using the token directly. The defense to this, HTTP only cookies. JavaScript can't read it. The cookie exists and is sent with requests, but it's invisible to JavaScript. Cross-site scripting can still perform actions as the user, but cannot extract the token itself. And CSRF. A malicious site tricks the user's browser into sending a request to your site with the user's cookies attached. The server sees a legitimate session. The defense to this, set same site as lags. Cookies are not sent on cross-origin sub-resource requests from third-party sites. Most CSRF attacks require XHR or form submission. Lags blocks those while allowing top-level navigation like clicking a link. Session fixation. An attacker sets a known session ID before the user authenticates. If the session ID isn't rotated after login, the attacker knows the valid token. The defense for this? Supabase rotates session tokens on every login. The pre-auth session is invalid after authentication completes. And we have credential stuffing. Automated scripts try username and password combinations from breached databases. The defense to this is rate limiting on the login endpoint combined with TOTP. Even a correct password doesn't complete authentication without the time-based code. HTTP only cookies versus local storage. The case against local storage for session tokens is a single line of JavaScript. An attacker who injects a script into your page through any cross-site scripting vector, including a compromised third-party dependency, writes one fetch call that reads localStorage get item supabase.auth token and posts it to their server. That's the complete attack. The token is now in the attacker's possession. They can log in as the user from any device from any IP address, and the session will be valid until it expires or is manually revoked. An HTTP-only cookie stores the same token, but JavaScript can't read it. The document.cookie returns an empty string if all cookies are HTTP only. The same cross-site scripting attack fails. There's nothing to read. The cookie exists and is sent with every request to your domain, but the JavaScript runtime can't access it. The server sets the cookie with all 4 required attributes: HTTP only, secure, same site, lags, the path, and the max age. Secure means the cookie is only transmitted over HTTPS. Yes, same site lacks handles CSRF. Session cookie attributes. There are 5 attributes, each closing a specific attack vector. Missing any one is a security regression. HTTP only. JavaScript cannot read the cookie. This prevents cross-site scripting, session token exfiltration. Remove it, and cross-site scripting steals the session in one line. Secure. Cookie is only sent over HTTPS. This prevents network interception or unencrypted connections. Remove it, and the token is exposed on any HTTP request, including over public Wi-Fi. Yep, same site to lags. The cookie is not sent on cross-origin sub-resource requests. This prevents most CSRF patterns. Remove it, and cross-site request forgery attacks become feasible. The path. Cookie is sent on all paths. Narrow this incorrectly, and logged-in users appear anonymous on certain routes. A 7-day session lifetime for your max age. The balance between relogin friction and the exposure window of a stale session. Have it too long, and a compromised session persists for too long. Too short, users are constantly re-authenticating. Supabase session architecture. The session management architecture has 3 layers. This is what I'd call a session sandwich. Firstly, we have the middleware that runs on every request before any server component renders. It reads the session cookie, calls getUser to verify the JWT with the Supabase auth server. This refreshes the access token if it's expired and sets the refresh token in the response cookies. By the time any server component runs, the session is already verified and fresh. We have server components. These call getSession, not getUser. After middleware has done the verification, getSession reads the JWT from the local cookie and decodes it locally. No network call. The token is already fresh because middleware refreshed it. Here's a practical rule concerning middleware. The middleware calls getUser once per request. Server components call getSession after. Never call getUser in a server component. That's 2 auth network calls page per load. And client components. These receive the session passed as props or via the Supabase client. They can call signout. They cannot read HTTP only cookies, which is the security property we want. The getUser versus getSession distinction matters for security. GetUser makes a network request to Supabase to verify the JWT is still valid. It catches revoked sessions that haven't expired yet. GetSession decodes the JWT locally without server verification. It trusts the local token. In middleware, use getUser. In server components after middleware verification, getSession is safe and avoids an extra network round trip. And then we have to make a distinction that we're using proxy, but it still serves the purpose for what most people understand as middleware. Without further ado, we'll continue. The auth flow. When a user logs in with email and password, Supabase auth returns 2 tokens, an access token and a refresh token. The access token is a JWT with a 3600 second, 1 hour lifetime. It's short-lived by design. If it is intercepted, it's valid for at most 1 hour. The JWT claims includes user ID, email, role, and session ID. The refresh token is an opaque string stored as HTTP-only cookie with a 7-day lifetime. It's used only to obtain new access tokens, and it's rotated on each use. Rotation is the critical security property. When Supabase detects a refresh token has been used more than once, which happens if a stolen token is used while the legitimate user also uses it, it revokes the entire session family. Both the attacker and the legitimate user are logged out. The legitimate user is alerted and can re-authenticate knowing their session was compromised. This means a stolen refresh token has a narrow window, from the moment of theft to the moment of either the attacker or the legitimate user use it. After first use, the token is invalid. TOTP with Supabase. Supabase provides native TOTP support. There's no external library, no custom token storage. Okay, so for enrollment, you call Supabase's auth MFA enroll. The factor type is TOTP. The response includes a QR code URL and the raw secret. Display the QR code for the user to scan in their Authenticator app. After they scan it, ask them to enter the first code to confirm enrollment. Call Supabase auth MFA, challenge and verify. If verification succeeds, TOTP is active for that user. For login flow, the user submits email and password via sign in with password. If MFA is required, the response returns session null, a signal that the authentication is at AAL1 and needs a second factor. Redirect to the TOTP entry screen. The user enters their 6-digit code. A call to Supabase auth MFA challenge is made to get a challenge ID. Supabase auth MFA verify. If verification succeeds, the session is elevated to AAL2. Supabase uses authenticator assurance levels as defined in the NIST guidelines. AAL1 is password only. AAL2 is password plus a second factor. When you require AAL2 in middleware, users without an enrolled second factor are redirected to set up one. Account enumeration. Account enumeration is the attack that most developers don't think about because it doesn't look like a security failure. It looks like the helpful error message. When a user logs in with an unregistered email, the server responds no account with that email. When they log in with a registered email and a wrong password, the server responds wrong password. The difference tells an attacker which emails are registered. An automated script trying 10,000 email addresses from a breach database can identify every registered user on your platform by reading the error message. The result is a list of confirmed registered emails. This is useful for targeted phishing or credential stuffing. The same vulnerability appears in password reset flows. That email is not registered confirms absence. Check your email confirms presence. The correct password reset message is always, if an account exists with that email address, you will receive a reset link, regardless of whether the email is registered. So we have 4 mitigations. The generic errors, right? Always invalidate email or password. Never which one. Uniform password reset response. Rate limiting. 10 attempts per IP per 15 minutes makes bulk enumeration impractical, even if the error message differences remain. And timing normalization. Ensure the response time is the same whether the email exists or not, because timing differences can also reveal account existence. Signout has subtlety that catches developers. Clearing the local cookie is not the same as invalidating the session. If you delete the cookie client side by setting max age to 0, the cookie is gone from the browser. But the Supabase session record still exists. If an attacker captured the refresh token before signout, they can still use it to get a valid access token. The session persists on the server even though the user has signed out on the client. The correct signout, Supabase auth signout. This makes a request to Supabase auth to invalidate the session server side, then clears the local cookies. Both the server side session and the local tokens are gone. Refresh token rotation. Each time the access token is refreshed, the refresh token is rotated. The old one is invalidated, the new one is issued. If an attacker steals a refresh token and uses it before the legitimate user does, the legitimate user's next refresh attempt fails. Supabase detects the reuse and revokes the entire session family. Both the attacker and the user are logged out. If the user uses it first, the attacker's stolen token is immediately invalid. So summary, authentication is a threat model, not a checklist. Authentication is a threat model, not a checklist. HTTP only cookies over local storage. JavaScript can't read or exfiltrate an HTTP only cookie. Cross-site scripting still works but cannot steal the session token for use elsewhere. All 4 cookie attributes, HTTP only, secure, same site, path, max age are required. Missing any one is a security regression. The session sandwich middleware calls. Get user once per request, refreshes the session, Sets the cookie. Server components call get session after. There's no extra network call. The token's already refreshed. Never refresh in a server component. TOTP over SMS. TOTP is tied to a physical device and a shared secret. The 30-second window and plus or minus clock skew tolerance are correct by design. Marked codes are used after verification to block a replay. Generic error messages everywhere. Invalid email or password. Never reveal which was wrong. Password reset always. If an account exists, you will receive an email. Rate limit all auth endpoints. Sign out requires server-side invalidation. Supabase auth sign out clears both the local cookie and the Supabase session. Client-only cookie clearing leaves the server session valid for a stolen token. For a client, authentication on this platform uses HTTP-only session cookies managed by Supabase, enforcing secure defaults without custom session logic. MFA is available via TOTP. The session refresh lifecycle runs in Next.js middleware, the proxy. Server components read already refreshed tokens without additional network calls.